Compositions of generating functions. How could we possibly define the composition of two generating functions? Assume for simplicity that f of x is equals to 1 over 1 minus x, which is equals to 1 plus x squared plus x cubed, and so on, and let g of x be any generating function. Our knowledge of the composition of functions suggests that f of g of x should be defined as 1 over 1 minus g of x, which is equals to 1 plus g of x plus g of x to the square plus g of x to the cube, and so on. It is here that the problems could start. The sum of infinitely many power series is defined only if for each n the coefficient of x to the n is 0 in all but a finite number of summands. In our case, this will happen if and only if the constant term of g of x is 0. Indeed, in that case, g of x to the n is divisible by x to the n. Thus, there are at most n-1 summands that contain x to the n-1, and this holds for all n. Therefore, f of g of x is defined in this case if f is a formal power series other than 1 over 1 minus x. The same argument holds. This is the basis of the following definition. Definition 8.12. Let f of x equals to the summations of fn times x to the n summing for all n which is greater than or equals to 0 be a formal power series, and let g be a formal power series with constant term 0. Then we define that f of g of x equals to the summations of fn of g of x to the n, fn times g of x to the n summing for all n which is greater than or equals to 0, which is, if we expand the terms, that will be f0 plus f1 times g of x plus f2 times g of x to the square plus and so on. The following theorem is a major application of compositions of generating functions. Theorem 8.13. Let an be the number of ways to build a certain structure on an n-element set, and let us assume that a0 is equals to 0. Let hn be the number of ways to split the set n braces into an unspecified number of disjoint, non-empty intervals. Then build a structure of the given kind on each of these intervals. Set h0 equals to 1. Denote a of x is equals to the summations of an times x to the n summing for all n which is equals to summing for n which is greater than or equals to 0, and h of x is equals to the summations of h n times x to the n summing for all n which is greater than or equals to 0. Then h of x is equals to 1 over 1 minus a of x. Note that unlike in theorem 8.5, here we do not allow empty intervals. The reason for this is that if we did, we would have infinitely many ways to split up braces as we could insert as many empty intervals as we like. This problem did not arise in theorem 8.5 because we only had a specified number 2 of intervals here. Proof of theorem 8.13. It follows from theorem 8.5 that a of x to the k is the generating function for the number of ways to split n braces into exactly k intervals. Then to build a structure of the given kind of each interval. Summing over all k, we get the summations of a of x to the k summing for all k which is greater than or equals to 1. As a0 is equals to 0, none of the power series a of x to the k has a non-zero constant term. On the other hand, h of x has constant term 1 by definition. This shows that h of x is equals to 1 plus the summations of a of x to the k summing for all k which is greater than or equals to 1, then which is equals to the summations of a of x to the k summing for all k which is greater than or equals to 0. because we just absorbed the term 1. Then, by definition, which will be equals to 1 over 1 minus a of x. Example 8.14. All n soldiers of a military squadron stand in a line. The officer in charge splits the line at several places, forming smaller non-empty units. Then he names one person in each unit to be the commander of that unit. Let Hn be the number of ways he can do this. Find a closed formula for Hn. Solution denoted by Hk the number of ways the officer in charge can proceed. Let Ak be the number of ways to choose a commander from a unit of k people. Then clearly Ak is equals to k, and therefore A of x is equals to the summations of k times x to the k, summing for all k which is greater than or equals to 1, which is x over 1 minus x to the square, as we have computed in example 8.6. Then theorem 8.13 applies, and we get that h of x is equals to 1 over 1 minus a of x, which is equals to 1 over 1 minus x over 1 minus x squared, which is equals to 1 plus x over 1 minus 3x plus x squared, where h of x is the generating function of the sequence Hn braces with n which is greater than or equals to 0. The evaluation of the fraction 1 over 1 minus 3x plus x squared is somewhat more complicated than in the earlier examples. We will use the method of partial fractions. The roots of x squared minus 3x plus 1 are alpha equals to 3 plus square root of 5 over 2, and beta equals to 3 minus square root of 5 over 2. Therefore, we want to obtain 1 over 1 minus 3x plus x squared in the following form. 1 over 1 minus 3x plus x squared is equals to 1 over x minus alpha times x minus beta, which is equals to a over x minus alpha minus b over x minus beta. After cross-multiplying, we get that 1 is equals to a minus b times x minus a beta plus b alpha. Therefore, we must have a is equals to b, and b times alpha minus beta is equals to b times square root of 5, which is equal to 1. So a is equals to b, which is equals to 1 over square root of 5. So this yields that 1 over 1 minus 3x plus x squared is equals to 1 over the square root of 5 times 1 over x minus alpha minus 1 over x minus beta. Note that alpha times beta is equals to 1. Therefore, we can multiply both the numerator and the denominator of the first, respectively second member in the parentheses by alpha and respectively by beta. After routine steps, we get that 1 over 1 minus 3x plus x squared is equals to 1 over the square root of 5 times alpha over 1 minus alpha x minus beta over 1 minus beta x. Therefore, the coefficient of x to the n in 1 over 1 minus 3x plus x squared is 1 over the square root of 5 times alpha to the n plus 1 minus beta to the n plus 1. Thus, the coefficient of x to the n in h of x is 1 if n is equals to 0, and hn is equals to 1 over the square root of 5 times alpha to the n minus beta to the n if n is greater than 0. Would you have guessed that our answer to this problem that was defined totally within the kingdom of integers will involve powers of alpha which is equals to 3 plus the square root of 5 over 2, and beta equals to 3 minus the square root of 5 over 2. The first few values of the sequence Hn are starting at H1, 1, 3, 8, 21, 55. These numerical data may be helpful in some of the exercises. In Theorem 8.13, we first split embraces into non-empty intervals, then we take a structure of the same kind on each of these intervals. However, we do not take a structure on the set of the intervals. Translating this to our example, the officer in charge did not ask the units to choose a unit on duty or to form a new line. The following theorem generalizes Theorem 8.13 in that direction. Theorem 8.15. The compositional formula. Let An be the number of ways to build a certain structure on an n-element set and assume A0 equals to 0. Let Bn be the number of ways to build a second structure on an n-element set. And let B0 equals to 1. Let Gn be the number of ways to split the set n braces into an unspecified number of non-empty intervals. Build a structure of the given kind on each of these intervals, and then build a structure of the second kind on the set of the intervals. Set G0 equals to 1, denoted by a of x, b of x, and g of x, the generating functions of the sequences an braces, bn braces, and gn braces. Then g of x is equals to b of a of x. Proof. Let us assume that we split n braces into k intervals. Then there are bk ways to take the structure of the second kind on the k-element set of these intervals. The product formula shows that the generating function for the number of ways to take a structure of the first kind on each interval is a of x to the k. Therefore, the contribution of this case to g of x is bk times a of x to the k. Summing over OK, we get that g of x is equal to the summations of bk times a of x to the k, summing for OK, which is greater than or equals to 0, which was to be proved. Example 8.16. All n soldiers of a military squadron stand in a line. The officer in charge splits the line at several places, forming smaller non-empty units. Then he chooses a possibly empty subset of the newly formed units for night duty. In how many different ways can he do this? Solution. Let us keep the notation of Theorem 8.15. Then AK is equal to 1 for OK which is greater than or equals to 1. As there is one way to put the trivial structure, that is to say no structure at all on the individual units. Furthermore, Bm is equal to 2 to the m as we simply choose a subset of the set of all intervals. Therefore, a of x is equal to x over 1 minus x, and b of x is equal to 1 over 1 minus 2x. So, g of x is equal to b of a of x, which is 1 over 1 minus 2x over 1 minus x, which is equal to 1 minus x over 1 minus 3x, which is equal to 1 over 1 minus 3x minus x over 1 minus 3x. So g of x is equal to the summations of 3n times x to the n, 3 to the n times x to the n, summing for all n which is greater than or equals to 0, minus the summations of 3 to the n minus 1 times x to the n, summing for all n which is either greater than or equals to 1, which is equals to 1 plus the summations of 2 times 3 to the n minus 1 times x to the n, summing for all n which is greater than or equals to 1. Consequently, if n is greater than or equals to 1, the officer in charge has 2 times 3 to the n minus 1 options.